Within the last decade, additive manufacturing has taken off, vastly increasing in popularity from 3D printing hobbyists to some of the world's largest manufacturers like NASA and Honda. The popularity of 3D printing can be attributed to the extreme customizability and relative low cost. These factors combined make 3D printing an ideal choice for all stages of production, from prototyping to final design, depending on the use case. The flexibility in 3D printing comes from the variety of variables that go into the process, including printing technique, printing material, infill pattern, infill percentage, and print orientation. We wanted to know which configuration of these variables produced the strongest parts. To narrow the scope of the experiment, we decided to only focus on one printing technique and test only the two variables we believed would have the largest effect on the strength of the part. The printing technique we chose is called fused deposition modeling, or FDM. This operates by extruding a filament of printing material, often plastic, through a heated nozzle into layers that slowly rise to form the desired shape. We chose this method because of its accessibility and because filaments can be a variety of different materials. Printing material was one of the factors we identified as potentially having the largest effect on the strength of the part. We selected three materials to test: polylactic acid, or PLA, which is a brittle, lightweight material that was chosen for its popularity in the 3D printing space; thermoplastic urethane, or TPU, which is a rubberized plastic that we chose for its ductility and strength; and polyethylene terephthalate glycol, or PETG, which was chosen for its durability despite its brittleness. The other variable we wanted to test was the infill pattern and how the part's internal supports affected the strength of the print. We chose three infill patterns to test: a grid pattern, which is widely used as a default infill pattern; a cubic pattern, which seeks to fill the internal geometry with angled cubes; and a gyroid pattern, which utilizes a wave-like shape for dynamic loads. For the other variables that we chose not to test, all of the prints contain the same 15% infill and were all oriented during the tests, facing the same direction that they were printed in. With three different materials, each with three different infill patterns, we had a total of 9 separate groups to evaluate.
In order to generate a 3D model of the part, we used SOLIDWORKS to model the cubes with arrows, and then exported an STL file to a slicing software where the slicer breaks down the part into the path the 3D printer will take to create said part. This is saved as a G-code, or a series of coordinates that the bed and nozzle will use to complete the print correctly. The Prusa Mark IV 3D printer in the ITLL use an online server called 3D Printer OS because this service allows students to keep track of the progress of their prints as well as know when a printer is open and ready to be used. 3D Printer OS contains all of the main options for speed, infill, temperatures, and other settings. However, the software is only allowed to print one infill type per print. In the shown graphic, each cube contains a different infill. In order for this to happen, we use a slicing software called Prusa Slicer, which is made by the same company as 3D printers. After uploading the correct G-code to the printers, we only need three prints: a PLA print, a PETG print, and a TPU print, where 3D Printer OS would have required 9 separate prints. To be sure everything printed correctly, we had to configure the settings to the given material. For example, PETG requires a slower print speed than PLA to be a successful print. TPU is also a much slower print, as well as a higher nozzle temperature to be sure that it reaches the necessary temperature to extrude correctly and cure properly.
To test the strength of our 3D prints, we elected to print 1.5-inch cubes and test their compression strength with an Exceed E43 electromechanical press, which applies compressive forces using an electric motor and magnets instead of the hydraulic fluid typically associated with mechanical presses. The press we selected also records the data from the entire process, which we used for our analysis. We opted to measure compressive strength as opposed to tensile or torsional strength because we wanted to see how each infill pattern would handle compressive force, as well as how each material would react to compressive stress after being heated and formed through the printing process. Before testing, we hypothesized that the filament material would matter more for the compressive strength than the infill pattern, leading us to group the predictions by material and then within each group by the infill. We predicted that the strongest material would be PETG, then PLA, and finally TPU, and that the strongest infill pattern would be gyroid, followed by cubic, and then grid. In order to record the data acquired from the compression tester, a load cell was used. The load cell is able to measure the amount of force and convert this data to a digital form that we could analyze. We selected a 50 kilonewton load cell which would work well to cover the range of expected results. The orientation of the cubes was essential so that the tests were performed under as similar of conditions as possible. To ensure the correct orientation, an arrow was printed on the front of each cube facing up, so when testing, we made sure to keep the arrow on the front face in the correct direction. After loading the samples onto the compression plates, we began measuring the compressive force using the program TW Elite from NTS software. At a compression rate of 1 millimeter per second and a sample rate of 1000 Hz, each test took approximately 1 minute to complete. The PET-G and PLA cubes were permanently deformed after the testing, while the TPU was able to elastically return to its original shape. Here we have the compressive stress results for each material and infill pattern. From the NTS Exceed manual, we could find that the force accuracy of the E43 machine is within 1% of the applied force. Comparing the maximum forces for the grid pattern, which was the strongest infill, the maximum force for the PET-G was about 7,200 newtons, followed by the PLA at around 5,300 newtons, and lastly, the maximum force for the TPU was only about 320 newtons. On average, the results for the PET-G were about 2,000 newtons higher than the results for the PLA. The TPU results were a full order of magnitude lower than the other materials and did not even exceed 500 newtons. The material type does have a bigger influence on the results than the infill pattern, which aligns with the reasoning for our hypothesis. One interesting trend that we noticed was how the force affected each infill pattern. For the grid and gyroid infill patterns, the graph shows a sharper incline and decline in force. However, for the cubic infill pattern, the force inclines at a slightly less steep angle and does not drop off after the maximum nearly as much as the other infills. A conclusion that we can draw from this is the infill pattern is likely collapsing on itself and increasing the compressive strength after the maximum force has already occurred.
In our hypothesis, we predicted that the PET-G would be the strongest material, followed by PLA and then TPU. We also predicted that the gyroid infill would be able to withstand the most amount of force, followed by the cubic and then the grid pattern. Contrary to our hypothesis, our results showed that the strongest infill was in fact grid, followed by the cubic and then the gyroid pattern. Our hypothesis was, however, correct in that the PET-G would be the strongest, second by PLA, and that TPU would be the weakest. For our compressive test, the most simple infill pattern prevailed compared to using more complex infill designs. However, PLA being the most popular material, performed comparably well to the much more expensive PET-G. This is not to say that these patterns and materials do not have their place in 3D printing. However, these tests did show why the grid pattern is the default setting and a popular choice for engineers. These tests did not cover the tensile or torsional stresses that could be applied to these materials and infill patterns. This would require different part designs and testing procedures, which could provide more insight into the strength of these different infill patterns and printing materials. In the future, it would also be very interesting to see how using different infill densities can influence the compressive strengths of each part using the same materials and infill designs, and how failure in the printing can occur.